before we start doing thermodynamics, we will have to take up a few gaseous laws. Some laws which are very important for you to understand, and you'll have to go through those laws properly, first of all. So let us do that. Beginning with what is an ideal gas, right? Ideal gas generally is a hypothetical gas It is a hypothetical gas in which the atoms or molecules do not have any attractive or repulsive forces. So then why have I given this as hypothetical gas? Because there is no such gas which can behave as an ideal gas under all conditions of temperature and pressure. So all gases, they behave ideally only under certain conditions. So under conditions of high temperature and low pressure, most of the gases behave ideally. The best part is the gases, the atmospheric conditions that we have, right, around us, the thermodynamic temperature about 298 kelvins, the atmospheric pressure 1 atm. These thermodynamic conditions that we have around us, these are the conditions for any gas. These conditions would be low pressure and high temperature conditions. As a result, most of the gases under normal conditions behave ideally. So all the gases, they behave ideally under normal conditions of temperature and pressure. The conditions that prevail around us, right? The gases have a tendency to behave ideally. Okay. Now, all ideal gases follow certain rules or laws, and they are called gaseous laws, right? So what are gaseous laws? So I'm putting gaseous laws. So all ideal gases, as I've told you, they follow certain rules, certain laws. They're called gaseous laws. The first law that I have to talk about is Boyle's law. The first law that we have is Boyle's law. Boyle's law is about relating pressure and volume of a gas. The law says that at constant temperature, for any gas, for any ideal gas at constant temperature, pressure and volume are inversely related. Pressure and volume are inversely related. And this is at constant temperature when T is equal to constant. We can also put it if we replace the proportionality sign by equal to sign, we have to put a K. Right? Now, here we find that if we try to plot a graph, how would it look like? For example, if I try to put up a graph here, like this, where I plot P against V at constant temperature, or P plotted against 1 upon V, the graphs would have different nature. The first one would look like this. Sorry. And the other one would be a straight line, and that would be like this. It should go from the origin. So the graphs are as simple as this. So, pressure against volume would be a kind of hyperbolic graph, and then we have a straight line graph where pressure is plotted against 1 upon V. Is that okay? Clear? So just remember Boyle's law, pressure and volume are inversely related. Then we have the second law that we have to do. That's called Charles' law. What is Charles' law? Let us take up. Charles' law relates volume and temperature. So we have to keep pressure constant. At constant pressure, volume is directly proportional to temperature. This is the law which tells you that volume and temperature are directly related to each other. Okay. You also have to know that if I want to replace proportionality sign by equal to sign, I will get V is equal to K into T. Now, this would be like V is equal to K into T. Now, you can even have a graph plot. You can plot graph of volume against temperature. The graph should be a straight line graph. The graph should be a straight line graph. And if you extrapolate this graph, at this point, you find that at this point, volume of any gas would become 0, and the temperature at which this happens is 0 kelvins. The temperature here has to be kelvins. When temperature is expressed in kelvins, we say it is absolute temperature. So when you give or express your temperature in kelvins, it is absolute temperature. So here the law tells you that at constant pressure, volume of a gas is directly proportional to its absolute temperature. Now here, if you extrapolate this properly, you find that this is the temperature at which volume of any gas becomes 0. Now remember, volume of any gas cannot become 0 as such, so this is just hypothetical. It is not possible that you decrease the temperature and volume becomes 0, which otherwise would mean this is the lowest possible temperature. This is the lowest possible temperature, and you cannot have temperature lower than this. And this is also not attained experimentally. It is not possible to attain 0 kelvins experimentally. So, hypothetically or theoretically, 0 kelvins, which is also equal to minus 273 0.15 degrees Celsius is called absolute zero temperature. This is called absolute zero temperature. Is that okay? Clear? The third point, the third law. This is Gay-Lussac's law. This law relates pressure and temperature. So we write at constant volume, pressure of a gas is directly proportional to its absolute temperature. Pressure is directly proportional to its absolute temperature. So we have, or we write pressure is equal to K into T, where K is a constant, proportionality constant. So graphically, this can be given like this. So if we put this as pressure and temperature, we may have a graph which would be a straight line graph. We will have a straight line graph. This is the Gay-Lussac's law. The fourth thing is Avogadro's law. This is Avogadro's law. The law tells you that this law has been already done by us and it has been expressed in a different way. Here we say different equal volumes of different gases under same conditions of temperature and pressure will have same number of molecules. So ideally, number of molecules would be same as number of moles. So I may in simple words, I may say at constant temperature and pressure, volume of any gas is directly proportional to its moles. Or we write V is equal to K into N. There is no graph here, but these are the four laws that you have to know. The statement of this Avogadro's law is already given in your notes. Equal volumes of different gases under same conditions of temperature and pressure would have same number of molecules. In other words, when you mathematically want to understand it, it means that when you have for any gas, if you keep temperature and pressure constant, then its volume would be decided by the number of moles. All okay? All right, let us do this. We can start with the combined equation. See, in order to understand a simultaneous effect of pressure, volume, and temperature on a gas, we have to combine these laws and get a combined equation. By combining all these laws, you will be able to know the effect of simultaneous change of pressure, volume, and temperature on gas. So, this equation that you derive by combining all these gaseous laws is called ideal gas equation. And any ideal gas will have to follow this equation. So, by combining...
Sir, straight line.
You don't need to draw a graph. By combining pressure, volume, by combining, let's say, Coyle's law, Charles' law, and Avogadro's law, one can derive a general equation which is followed by every ideal gas. This equation is referred to as ideal gas equation. So let us get that equation. We keep volume as a subject every time, so volume is proportional to 1 upon P. Volume is proportional to T. The first one is Boyle's law, second one is Charles' law, and third one is Avogadro's law. Right? This is Boyle's law. This is Charles' law. And this is Avogadro's law. Now we combine all of them. Therefore, we get V proportional to N into T by P. Or we write PV proportional to NT. Therefore, we can write PV is equal to nRT. This is a very, very common equation that you have. Here, R is a constant and it can be used for any gas. So it is called universal gas constant. Universal gas constant. What should be the value of R? R is equal to, first of all, 0.0821 liter atmosphere upon mole Kelvin, which is equal to 0.0831 liter bar upon mole Kelvin, which is also equal to, depending on the unit that you want, 8.31 joules per mole Kelvin, which is equal to 1.98 calories per mole Kelvin.
Usually joules per mole Kelvin.
Yeah, joules per mole Kelvin you can use, or you can use any one of these, depending on whether the pressure is given in ATM or bar. Also, 1 liter atmosphere. Liter atmosphere together is a unit for work or energy. So, liter atmosphere is equal to 101.3 joules. 1 liter bar is equal to 100 joules. So these are all different things that you have to remember and know. These are fundamental things. After having understood all these things related to thermodynamics, let us start with the first part, and that be like what exactly is thermodynamics? So thermodynamics is a branch of science which involves in study of different forms of energy and the quantitative relation between them. So a branch of science which involves in studying of different forms of energies and quantitative relationship in between them. Clear? When this study is restricted to chemical systems, we call it as chemical thermodynamics. Chemical thermodynamics, first of all. So, when this study is restricted to chemical systems, it would be called chemical thermodynamics. So that would be called chemical thermodynamics. So we are doing basic terms related to thermodynamics. The first is the first one is system and surroundings. This is the first part, system and surroundings. So what is a system? What is a surrounding? So here we write system is a part of universe undertaken for experimental observation. So by definition, a part of universe which is undertaken for experimental observations. So what exactly is surroundings? What exactly is surroundings? So surroundings would be entire universe excluding system. Entire universe excluding system. So ideally, you can have system and you can have surroundings, and this is a boundary which separates them. What is this boundary which separates them called? It is called a wall or a boundary. They also call it a boundary. Simple. Wall or boundary, what can it be? It can be conducting or it can be non-conducting. Conducting wall is the one which allows energy to be conducted between system and surroundings, and non-conducting would not allow energy to be conducted between system and surroundings. So any wall which is conducting is referred to as diathermic wall, and any wall which doesn't allow that to happen is called adiabatic wall. All clear?
So can you explain conducting and non-conducting?
Basically, conducting would mean the wall allows energy to be conducted or to be exchanged between system and surroundings, and non-conducting would not allow to happen, would not allow energy to be exchanged between system and surroundings. So this is what we have. Now, regarding systems, we have three different types of systems. So you have three different types of systems. One is called open system. Then we have a closed system. And then we have a isolated system. Open system, closed system, and isolated system. What exactly is an open system? Energy and matter can be exchanged between system and surroundings. What is the best example of such a system? Hot water taken in a glass. Hot water taken in a glass is a very good example of this. It can exchange energy, it can exchange matter, everything with the surroundings. Closed system. Energy can be exchanged, but matter cannot be exchanged. Between system and surroundings. What is the best example that you can give here? Hot water taken in a closed glass bottle. And what is an isolated system? Here, in such a system, neither energy nor matter can be exchanged between system and surroundings. Remember, a perfectly isolated system is very difficult to get. You cannot get a perfectly isolated system, but temporary, you can have an isolated system. How? Yeah, hot water taken in thermos flask. All right. So I hope this is clear to you all of what exactly things are. What do you think? Open system or closed system? What boundaries what kind of walls do they need? They need conducting walls, and therefore they need diathermic walls. What is the wall present in them? Diathermic wall. And what is the what kind of wall is present here? You have adiabatic wall. So while open system and closed system would need diathermic wall, isolated system would be having adiabatic wall. All okay, everyone? So this is about the system and the surroundings. Now we go to the next part, and that is state of a system, state variables or state functions. Okay, let us go to that. What exactly is a state of a system? State of a system would mean condition of a system expressed by some of its measurable properties. Like temperature, pressure, volume, etc. So when you describe condition of a system using some of its measurable properties like temperature, pressure, etc. So give temperature of a system, give pressure of a system, give its volume, etc. These measured values, they describe the state of a system. So that's called the state of a system. Then you have state variables. So measurable properties like pressure, volume, temperature, etc. are also referred to as state variables or state functions. These measurable properties are also referred to as state variables or state functions. Why so? That's because these measurable properties, like state variables or state functions, why are they called state variables? Because any change in their values will change state of a system. Any change in the values of all these measurable properties will change the state of a system. That is why we call them as state variables. And state functions, what are they? State functions. So here we find any change, or let's say, their values depend only on initial and final states of a system. their values depend only on initial and final states of a system, but not on the path taken by system. To go from initial to final state. So ideally, all these state variables are also referred to as state functions due to simple reason that their values depend only on initial and final states of a system, but they would not depend on the path followed by the system to go from initial state to final state. And that is why we have state of a system, state variables or state functions. I hope this is all clear, done, right?
And these are state variables and functions.
See, there are certain properties of a system. I'm talking about measurable properties. There are certain measurable properties of a system. We talked about measurable properties, right? State variables or state functions, measurable properties, right? So, there are certain measurable properties which depend on the amount of matter which is inside a system. And if matter of a system changes, the value of these properties would also change. And then there are certain measurable properties, they would not depend on the quantity of matter inside the system. They would remain same if matter is changed. I would give you some examples and explain this to you. First of all, these are the properties which depend on quantity of matter in a system. And intensive properties which are independent of quantity of matter in a system. So those properties, those measurable properties which depend on quantity of matter that a system has, they are called extensive, and those which do not depend on quantity of matter in a system, they are called intensive. I can give you a simple example to understand this. Suppose this is a container, right, in which we have a gas. The gas will have a pressure of, let's say, 1 atm. The temperature is T kelvins, and volume of the gas is V liters. This is the pressure. Pressure is equal to 1. Volume is V liters. Now suppose, and there's a gas inside, right? Now suppose if I divide this gas by putting a partition, I divide it into two compartments. What would happen? Temperature would be T kelvins in both. Pressure would also remain 1 atm in both. What would change? Volume will become V by 2 liters. Volume would become V by 2. So a measurable property like volume changed when the quantity of matter changed. Whereas some measurable properties like pressure and temperature did not change in spite of your system divided into two parts. When quantity of matter inside the system was made half, volume became half, but your temperature and pressure did not change. So properties like temperature and pressure, which do not depend on the quantity of matter, we put them under intensive properties. And properties like volume, right, we call them as extensive properties. Do you understand this now? So then take some examples here. In extensive, we have volume, we have mass, we have heat capacity, and all the thermodynamic properties. You have a lot of other thermodynamic terms which you would be knowing a little later on in this chapter. One is called internal energy. Enthalpy, entropy, free energy, etc. They all come under extensive properties, right? They all come under extensive properties. I can give you some intensive properties. So first of all, what is heat capacity? Heat capacity is like the heat needed to change the temperature of any substance by 1 degree Celsius. Heat needed to change the temperature of any substance by 1 degree Celsius. Now, if you change the mass of that substance, if you increase the mass or decrease the mass, the amount of heat needed would also change. Why? Because if you increase the mass, you will need more energy. For the same substance, you will need more energy to increase its temperature by 1 degree Celsius. And if you decrease its mass, you will need less energy to increase its temperature by 1 degree Celsius. So ideally, heat capacity, which is denoted by C, simple C, that's extensive property. Samajh aave chhe barabar? Now, because in heat capacity they do not mention mass, they do not mention anything. Yes.
Container માં partition કરે તો pressure માં change કરે.
Pressure માં change એટલે ના આવે. Just we have intensive properties. હવે જુઓ કેટલી heat capacity. આપણે પહેલા તો we talked about two properties, right? Pressure temperature. You also have, remember, density. You may take 1 liter of water or 10 liters of water. What would be its density? Its density would remain the same. pH. pH of pure water, what is it?
0.
pH of pure water is 7.
Sorry.
So if pH of pure water is 7, you may take 1 liter of water or 10 liters of water, pH would remain same. You have molarity. What is molarity of pure water? 55.55. We've defined that, right? 55.55. That's the molarity of pure water. You may take 1 liter or 10 liters, it is always 55.55. Molarity would never change. Clear or no? You have specific heat capacity. Specific heat capacity is always given per 1 gram. Simple heat capacity is given for any mass, but specific heat capacity is given only for 1 gram.
1 gram no temperature.
Per 1 gram, yeah. So that's specific heat. Or you can have molar heat capacity. It's given only for 1 mole. So your system may have any matter in it. It is always defined per 1 mole. You can have surface tension, viscosity, etc. They all are intensive in nature. These are a list of See, surface tension and viscosity, they're also basically, in a way, if you understand them, there would be force given per unit area. So there'd be like force per unit area. Is that okay? So that'd be, again, the same intensive properties. All right. So you have the third category, extensive and intensive properties. The fourth would be a process. What is a thermodynamic process? So we need to understand what a thermodynamic process is. Generally, when a state of system changes, we say a process has occurred. So, a process occurs when state of system changes. A process occurs when state of system changes. And how many types of processes do we have? So there are different types of processes. One, isothermal process. This is a process which occurs at constant temperature. So any process which occurs at constant temperature is called isothermal process. Two, isobaric process. Occurs at constant pressure. Then we have isochoric process. Isochoric processes occurs at constant volume. And adiabatic process, you have to remember all of this. A process in which heat cannot be exchanged between system and surroundings.
સર તો આઇસોથર્મલ અને એડિયાબેટિકમાં ફરક જ શું?
Let us plot them all together. So we are putting a pressure volume graph to plot these processes. This is pressure here and this is volume here. So if you talk about a process in which pressure remains constant, it would go like this. And if you talk about a process in which volume remains constant, it would go like this. So this is like isobaric, and this here is isochoric. So while one is isobaric, the other is isochoric. See, you can see that the volume remains constant, it doesn't change. The pressure changes, but volume remains constant. Here pressure remains constant. Now we go to isothermal. Isothermal is, you've done the Boyle's law. At constant temperature, pressure and volume are inversely related. Did we do the graph also? That's the same thing, isothermal. You have it like this. This is isothermal. Now isothermal here. And what do we have here after isothermal? What do we have? There's adiabatic. In adiabatic, the problem is, look at this. When pressure decreases, volume increases. So here the pressure is decreasing and volume is increasing. Right? Now imagine that the system is not able to take heat from the surroundings. What would happen? With decrease in pressure, volume will increase, but at the same time temperature will also decrease. Temperature will also decrease. Here the temperature is not allowed to decrease because the system is continuously getting heat from the surroundings. Temperature is maintained constant. Do you understand this? In this process, as you decrease the pressure, volume increases. With decrease in pressure, the temperature also has to decrease because pressure and temperature are directly related. But then, as temperature decreases, in isothermal process, system starts taking heat from the surroundings. Right? However, in adiabatic process, what would happen? System is not allowed to take heat from the surroundings. So as pressure decreases, volume increases, but simultaneously temperature also decreases. So what would happen if temperature decreases? How are temperature and volume related to each other?
Inverse.
Directly related, volume proportional to temperature. Which means with decreasing temperature, the volume also decreases. So here two things happen. Decrease in pressure increases the volume, but because there is simultaneous decrease in temperature also, decrease in pressure increases the volume, that's correct. But because there is simultaneous decrease in temperature also, the volume will not increase as much. Because with decrease in temperature, the volume has to decrease. So pressure is decrease in pressure increases the volume, but decrease in temperature restricts that volume from increasing. Why? Because decrease in temperature would decrease the volume. So two effects, they operate in opposite directions. With decrease in pressure would increase the volume, but with decrease in pressure, temperature drops, and with decrease in temperature, the volume has to decrease. So the overall, if you understand the combined effect, you find that the decrease in volume in adiabatic process will be less as compared to decrease in as compared to the isothermal process, because in isothermal process the volume increases more. In adiabatic the volume increases less, because in adiabatic process temperature decreases, system is not going to get heat from the surroundings, so that decrease in temperature also starts decreasing the volume, and therefore overall the increase in volume is restricted. So you can see that for the same kind of pressure decrease, the increase in volume is less here. The increase in volume is more here. So that's how it is. So this is adiabatic. This is adiabatic. You have to know, all these properly, because this is important. How different processes differ from each other. Okay. Now we have the fifth point. That's reversible and irreversible processes. Okay. Based on the way any process occurs, based on how a process is executed, right? There are two different types of processes, reversible and irreversible. Okay, what is a irreversible process? What is an irreversible process? Right? This process occurs rapidly in one step. This process occurs rapidly in one step. Here, it cannot be reversed. Once it starts. So once it starts, it cannot be reversed. It is rapid. One step. Clear? And all real processes are irreversible. All processes that occur in our day-to-day life, they have to be irreversible. I'll give you an example here. Suppose we have a cylinder with a frictionless piston. Right. And there is a gas inside. The pressure of the gas inside is, let's say, 2 atm. Now, let's say we have P external, pressure external, which is more than the pressure of gas, and let's say external pressure is, let's say, 4 atm. So what would happen? The piston would move in, and it would keep on moving in till the pressure inside will become 4 atm. At that point, we say a mechanical equilibrium is established. So obviously, volume and pressure are inversely related. So if you want to have pressure getting doubled, the volume has to become half. So in one step, the volume would become half. Piston would be forced to move in single step. This is an irreversible process. A similar process, if it is carried out reversibly, I'd show you what happens. So first of all, irreversible process is a rapid process. You cannot stop a process once it begins. Now, what is a reversible process? This occurs at an infinitesimal slow rate. At every microscopic stage, system attains equilibrium with surroundings. At every microscopic stage, system attains equilibrium with surroundings. So it takes place in infinite number of steps, and at every microscopic stage there is an equilibrium established between system and surroundings. This is a hypothetical process. Which means that such a process cannot be actually carried out. I'll tell you why we have to understand this. It's very important to know these processes. But yes, this is a process which cannot be carried out in real life. However, you can try to have your process become reversible. There's always an attempt to make a process reversible. A perfect reversible process cannot be had because this is undefined thing, right? Infinitesimal slow. That's undefined. All right. Now, at every microscopic stage, there is an equilibrium between system and surroundings. So how would this take place? I've just given you an example of how this works. The same kind of thing. So you have the same kind of piston, and we have the external pressure P external, and then we have the gas inside, and pressure of gas is once again 2 atm. Pressure is 2 atm as before. Now, how would you carry out a reversible process of compression? You want to attain what? The pressure inside should become 4 atm, right? So what we do is, P external would be, let's say, initially 2.001. So what would happen? Piston would marginally move inside till the inside pressure would become 2.001. Then I would make the external pressure 2.002. I may define this as an infinitesimal slow process till my external pressure becomes equal to 4 atm. So this would, these are finite steps, as such you can calculate them, but otherwise if you consider qualitatively, this process is more or less, infinitesimal slow process. So you can have, such a process can be thought of as a reversible process. So in any reversible process, there are two differences here. The external pressure, during compression, external pressure, right, is slightly more than the internal pressure. So we can say that during compression, I'm just showing you all this, during compression, when you're compressing a gas in a irreversible process, P external is large and much higher than pressure of gas during compression. And in reversible process, P external is minimum possible value. Do you understand this? When you're compressing a gas, reversibly, the external pressure has to be only marginally more than internal pressure, every time. Whereas external pressure during irreversible process of compression, the external pressure will be much larger than the internal pressure. Do you understand this? And the reverse would become true for expansion. When the gas is expanding, irreversible expansion, the external pressure would be much lower than the internal pressure. And in reversible expansion, the external pressure would be marginally, or it has to be, during expansion, external pressure has to be only slightly lower than the internal pressure, which means external pressure will have its highest possible value. Do you understand this? So make a note of this, write this down in your books. During expansion, irreversible process, P external is much lower than pressure of gas. And reversible process, you find P external is the maximum possible value. So the P external would be maximum possible value during expansion, and during compression, P external would be minimum possible value. All clear? Internal energy. It is the sum of all possible forms of energies of any system, like potential energy, kinetic energy, which would be like rotational, vibrational energies. Etc. So, a sum of all possible forms of energy that a system can have, that the particle of any system can have, that molecules or atoms of any system can have. All that is internal energy, right? Because this is so complex, we can say that its absolute value cannot be found. Only changes can be calculated. So, absolute value cannot be found. So, you cannot get internal energy of a system. You can calculate only its changes. All clear? What is the symbol for internal energy? The symbol is U. It is a state function, and it is an extensive property. You know, state functions depend only on what?
Initial and
Final state. So, if you want to calculate change in internal energy of any process, it is internal energy of final state minus internal energy of initial state.
extensive property का है.
Internal energy will depend on, see, amount of energies. If you add the particles, every particle has energy associated with it. So the internal energy keeps on increasing as you add particles. So that is an extensive property. You say, look at this. Internal energy of any system can change. Internal energy of any system can change if one, matter is added or removed from system. 2, heat is given or removed from system. So we talk about work done in irreversible process. Clear or not? That's the first part, irreversible work. I told you that work is a path function, so irreversible work, you will have a different equation, and reversible work, you will have a different equation. So let us do that. In order to calculate work done in irreversible process, let us understand how this can be done. We start with consider 1 mole of an ideal gas. Consider 1 mole of an ideal gas taken in a closed cylinder, right? Let pressure of gas be P. You can also put it as P gas or just simple P. And area of cross section of piston be A. If initial volume of gas is V initial, VI we put it, V initial, and P external is the external pressure. P external is the external pressure. The piston first of all, irreversible work, irreversible compression will occur as P external should be larger than P of gas. You know that work done will be irreversible work. So work irreversible will be equal to force into displacement. Here, from the figure, the piston moves through a distance L. The piston moves through a distance L. Till pressure of gas P becomes equal to P external. So the piston keeps on moving in till the pressure of the gas inside becomes equal to P external. And for this, it has to travel a distance L, and final volume of gas is VF. So ideally, we find that the volume of a gas goes from initial VI to final VF. And you have to understand that the distance traveled by the piston is L, which is very, very important. Why am I doing all this? Because ideally you have to calculate irreversible work, which is given by the same thing, force into displacement. Displacement is L. But how do you calculate force? So here we put pressure is equal to force on gas upon area. Therefore, force should be equal to pressure into area. Pressure is P external and area is A because it is the area of cross section of the piston. The area on which external pressure is exerted is A. So pressure into area gives you force. Now we can have work irreversible should be equal to P external into A into L. But you have to know that from the figure, A into L is equal to change in volume. I would show you how, which is equal to Vf minus Vi, which is delta V. What is A into L? This is A and this is L. So this area, that's A into L. What is this area equal to? Change in volume, right? It was like initially it was Vi and now we have Vf. So change in volume is delta V and that's A into L. So ideally we get Vf minus Vi is equal to delta V and that be equal to change in volume. So now coming back to this, W irreversible is equal to P external into multiplied by Vf minus Vi. But Vf here, because during compression Vf is smaller and this is larger, which means this value has to be negative. In that case your work will be negative. But you know that during compression work is done on the system. Compression work, I told you that during compression work is positive. Did we do that? During compression work involves positive work. So work has to be positive. But when you do this here, you find that the work comes out to be negative. So in order to have this right sign convention, what we do is we take up W irreversible is equal to minus P external into delta V. The negative sign would take care of the right sign that the work should have. So yes, so negative sign allows correct sign convention for work. All right. So this is your basic thing. The first equation that you have to know. This is the first equation of compression. This is the work calculated under irreversible condition. And what is the formula that you have to remember? W irreversible is P external into delta V negative. Remember, how would you, if they give you a numerical and if they don't tell you what kind of process will this be, આ રિવર્સેબલ છે કે ઇરિવર્સેબલ છે કહેશે જ નહીં તો તમે શું કરશો? You will have to check the pressure. In irreversible process, the pressure always remains constant, same. Where you remember when we talked about reversible and irreversible process, I did give you some examples like, in irreversible process, the pressure was 4 atm constant throughout. But in reversible process, the external pressure would always be slightly more than internal pressure. So external pressure keeps on changing. Do you get this or not? So external pressure continuously changes. So whenever your pressure doesn't remain constant, right, it has to be reversible. When pressure remains constant, then it is irreversible. You have to understand these important things when you go through and read a numerical. These are all hidden things. Many a times they don't tell you anything about the process. Okay. So I think this is the first part that we've done and finished. We would continue doing this calculations and a lot of numericals next time because I have a full worksheet given numericals. Please bring your modules next time because I would be solving questions from your modules. So bring your modules.